Hi viewers, in this session we are going to see about the continuity equations for three different types of flows. So the topics I am going to discuss in this is, so what is the fundamentals in the continuity equation, and what is the continuity equation for one-dimensional flow and three-dimensional flow, and some mathematical derivations, and also how it will be for steady and unsteady flow, and what are the different applications of the continuity equation in pipeline, dams and river systems. So we will see the one by one. So first you should know that what is a one-dimensional flow and three-dimensional flow. So whenever if I am taking this, this is the final equation. The one-dimensional flow means the velocity will be varying in only in one direction. If I am taking the three-dimensional, it will be varying in all three directions. Okay. So now we will see the what is the continuity equation. So the principle behind this continuity equation is conservation of mass. So the law of conservation is used for finding this. So here if I am taking this for incompressible fluid, the cross-sectional areas increases, the velocity increases to maintain the constant mass rate. So this is the relation between the velocity and area. So what is the mass flow rate? The mass flow rate remain constant throughout the fluid flow means we are taking that the m equal to constant, that is a rho into VA is constant. And if I am taking this for one-dimensional flow, so the rate of flow, which is, if I am taking this is a pipe, this is a pipe 1 and pipe 2. Whenever the fluid is entering into this, if I am finding the rate of flow at 1, it will be equal to the mass flow rate at the leaving point also. Okay. So here for if I am taking the incompressible flow, the continuity equation is A1 V1 equal to A2 V2. So that is the discharge is same at point 1 and also point 2. So if I am taking this, the Q is the discharge and A is the cross-sectional area at 1 and 2, and the velocity that is a point 1 and 2. So if I am taking the one-dimensional flow, it is applicable for incompressible flow. So in that point, the A1 V1 equal to A2 V2. So if I am taking for the compressible flow, the density parameter will be also involved. So here if I am taking this finding the thing, first the control volume approach. So we are considering the volume of fluid at section 1 and 2. So if I am taking the steady flow condition, the mass of fluid at inlet is equal to mass of fluid at the outlet. Okay. So here the flow expression in the step 1, first we will calculate the mass of flow rate. The mass of flow rate is nothing but rho into AV. So for incompressible flow, this rho 1, if I am taking that both the section, the mass at section 1 is rho 1 A1 V1 and at 2 is rho 2 A2 V2. If it is for incompressible flow, the density is equal. So therefore the A1 V1 equal to A2 V2. So and if I am taking that for a three-dimensional flow. So here this is a continuity equation for the Cartesian coordinate, and we will do some derivations and we will take some small rectangular element, and we will find the velocity variation in x direction and y direction, is that since the 3D flow means the velocity will vary in all three dimensions. Okay. And here if I am taking this the derivation, first we will find the control volume. So that is, we will take one small element with a volume of dx dy dz, and we will find the mass flux through this phases. Okay. So if I am taking that the flux, the variation of mass, there will be the inlet will not be equal to outlet. So the net mass will be the summation of the difference between the the mass which is outlet and also the inlet, and it is applied for in all directions. Okay. So therefore here also we are using the conservation of mass, and if I am going for a steady flow, this density will not change with respect to time. Therefore this equation will become like this. So if I am going for the incompressible flow, this density is constant everywhere. So therefore the above equation will become dou u by dou x plus dou v by dou y plus dou w by dou z. So therefore if I am taking this equation, we are calling this a continuity equation for 3D flow. Okay, so we will see that how that the visualization techniques which are involved. So whenever if I am taking that computational fluid dynamics for flow complex analysis, and if I am taking some dye injection, so you can see that these are the patterns which are colored the traces. So here you can see that the different color shows the variation of the velocity, and also the particle image velocity, that is a PIV, also shown here, and this is a velocity field distribution, that is a CFT, and we will see that how that visualization techniques. So if I am taking some dye injection, so if I am inject some dye color into the water to trace the streamlines and to absorb the flow of water, and if I am taking the another the method is smoke injection. So we will introduce some smoke into the airflow, and you can visualize the turbulence and water patterns. So similarly, so mathematically we can compute the thing, and some of the advanced methods are there, like the CFT analysis, the simulation, you can do it. So this visualization will confirm the theoretical predictions, and also it reveals the complex flow phenomena. So these are all the topics I have covered. If I am taking this, where we are using, so we are whenever we are going for the water supply systems, where that the civil engineers who are working in government sectors, they should study the water supply. So wherever we are going, we have to design the water distribution networks and also the systems, and also the design the hydraulic structures like dams, spillway, reservoir, etc. And also the river engineering and the flood control also, this is very important. And the important thing is the why we are storing the water reservoir. There are so many the applications are there, the uses are there. The main important thing is the agriculture. Okay, and also we have to manage the sewage and drainage. So here these are the applications or for studying about this equation in the civil engineering. So thank you for listening this video. Thank you.